Alright folks, today we're going to start chapter 7, and I want to talk about the idea of relations and functions, and a couple more things about functions. Really the focus is on functions, but I'm going to start with relations since functions are a special type of a relation. And as a quick reminder, let me remind you about a Cartesian product because that's going to be important here. So, if A is the set, I don't know, 1, 2, and B is the set A, B, C, then remember the Cartesian product, A cross B, is all possible pairs, ordered pairs of objects, or of elements, where the first element is in A and the second element is in B. So we're going to have 1A, 1B, 1C, and then we're going to have 2A, 2B, and 2C. So that's a reminder of what a Cartesian product is. And a relation, I'll write down its technical definition, but we don't really think of it like this in some sense. So a relation is a relation, let me tell you, from what to what. Let's erase this. It's a relation from a set A to a set B is any subset of A cross B. But we don't really think of it like that. The way we usually think about it is elements of A are related to elements of B via some rule. And that's kind of the important bit, is the rule. So let me give you an example of what I mean. All right, let's let A be the set 2, 3, 5, and 9. And let's let B be the set 1, 4, and 11. And the rule is, and let's call that rule or relation, let's call it R. So I'm going to say A is related to B. And the way we write that, we just put an R because that's the name of our rule. That R is this R. So A is related to B. And kind of this here means is related to by rule R. If we had a different rule name, we'd use a different letter there. Exactly when. And here's the rule I'm coming up with, just as an example, when A plus B is prime. All right, so let's figure out what elements are related to each other. Well, a good way of doing this, especially with anytime you have ordered pairs, making a little chart isn't a bad idea. So let's go ahead. So we'll put the elements of A vertically and the elements of B horizontally. So A had 2, 3, 5, and 9. B had 1, 4, and 11. So we can make a little chart here. All right. So The first element is 2, 1. Well, 2 plus 1 is 3. Is 3 prime? It sure is. So we want this in our relation. So this is indeed in our relation. And we can do that with every pair. And I'm just going to write down the pairs that are indeed in our relation. The other ones I'm not going to write down. So, and just as a reminder, everything, every possible combination is A cross B. We're just looking for the ones that satisfy our rule. 2 plus 4 is 6, so 2, 4 is not in our relation. 2 plus 11 is 13, so 2 and 11 is in our relation. Okay, let's check with 3. 3 plus 1 is 4. 4 is not in our relation. 3 plus 4 is 7, so 3, 4 is in our relation since 7 is prime. 3 plus 11 is 14. 14 is not prime, so it's not in our relation. 5 plus 1 is 6. 6 is not prime. 5 plus 4 is 9. 9 is not prime. 5 plus 11 is 16. 16 is not prime. Okay. 9 plus 1 is 10. 10 is not prime. 9 plus 4 is 13. 13 is prime, so we have 9, 4. And 9 plus 11 is 20, and 20 is not prime. So these are all the elements of A and B that are related to each other. So the set A is 2, 1, 2, 11, 3, 4, and 9, 4. And remember, these are ordered pairs. So the first element is always from A, and the second element is always from our set B. So that's how this works. Actually, let me write them in capital letters. That'll probably look a little bit better. So the first element is, of course, from A, and the second element is from B for all of these pairs. That's how A cross B works. There's another way of looking at these, which I'll show you. You can draw little graphs to help you out here. So another way of viewing relations. Well, we can put all the elements of the set A over here. They are 2, 3, 5, and 9. And we can put all of the elements of B over here. 1, 4, and 11. And we can draw arrows between the elements that are related. So we know 2 is related to 1, 2 is related to 11, 3 is related to 4, and 9 is related to 4. So this is another way of viewing the set R. So each arrow gives you the ordered pair. On the left is the first element of your ordered pair, and on the right is the second element of your ordered pair. So that's a good way of looking at relations as well. So this will be important in a little bit. For now, I just want to point out that kind of how many arrows are going from or to one of these objects, elements in these sets, doesn't matter. 2 here is related to 2 different elements of B. Awesome. 5 is related to no elements of B. And 3 and 9 are related to 1. Doesn't really matter. Same with the elements of B. 4 is related to elements of B. And 1 and 11 are related to exactly 1. So you can have elements in A or B related any number of ways that your rule calls for. Let's do one more example, and then we'll talk about a special type of rule. So let's say the set A are going to be... All right, let's look at this example. Let's say A is going to be all natural numbers, and so is B. B is also going to be all natural numbers. In our relation, I already used the letter R. Let me use the letter S. So I'm going to say that the relation S is going to be defined by an element of A is related through the element, or through the relation S to an element of B if there is a rectangle with area A and perimeter B. Okay, obviously there's an infinite number of elements in both A and B, so I can't draw every element of our relation. But I can ask if certain elements are in our relation. Well, let's do a couple just to see what's going on, and then I'll ask the question. So, let's draw it out. A is going to be all our numbers. So here are all the natural numbers. B, again, is all natural numbers. Well, let's take an element like 10 in A. 10 is a natural number. We're thinking of A as, we're thinking of this as like area, and B we're thinking of as perimeter. Oh, let me write that again. Perimeter. Oh, wrong one. Okay. So, what rectangles have area 10? Well, kind of the easiest one to think about is if something is 10 by 1, that obviously has area 10 for rectangle, length times width. 10 times 1 is 10. Okay? Well, what's the perimeter of this? Well, the perimeter of this is 2 times 10 plus 1. So we have 2 sides of length 10 and 2 sides of length 1. So 10 plus 1 plus 10 plus 1. So 10 plus 1 times 2, which is 11 times 2, which is 22. So I know 10 is related to 22. Well, is there anything else? Well, let's see. What about something like this? Something that is 5 by 2. Well, the area is still 10, but the perimeter is 2 times 5 plus 2. So we have 2 lengths of 5 and 2 widths of 2. So that's 2 times 7, which is 14. So 10 is also related to 14. So we have a number that's related to at least 2 numbers. In fact, I will tell you that they're the only 2 numbers that 10 is related to. You can check. What about something like 7? What's 7 related to? Well, if you think about it, the only type of rectangle you can make that has area 7, where your numbers are just whole numbers for the lengths of sides, is 1 by 7, or 7 by 1. And this has perimeter 2. So this has perimeter 2 times 7 plus 1, 2 sides of 7 plus 2 sides of 1, which is 16. So 7 is related to 16, and that's it. Well, something like, oh, let me think of something, maybe, let's do 12. So let's draw all the rectangles that are related, that have area 12. And so really we're just looking for all possible factors of 12. So 1 times 12 gives you 12, and that you can check has a perimeter of 26. I'll do perimeters here in red. You could have something that is 3 by 4, and that has perimeter 14. And you could have something that is, these aren't drawn to scale, but that's okay. I'll write the numbers in. 2 by 6, which has perimeter 16. And that's it. They're all the factors of 12. 1 times 12 is 12. 2 times 6 is 12. 3 times 4 is 12. And that's all you got. So 12 is related to 3 things. 12 is related to, well, it's related to 14, so we can draw an arrow there. It's related to 16, and it's related to 26, which I'll put down here. So 12 is related to those 3 numbers. So that's how this relation works. And you could think any whole number you like here, you could draw a rectangle with that area. You just have one side that number and the other side 1. So every element in A is going to have an arrow to an element of B. But not the other way. If you notice, for all perimeters, we're adding 2 times the length plus 2 times the width. So it's an even number plus an even number. We're going to get an even number. So any number like, say, maybe 7 over here, there is no rectangle where the sides are all whole number lengths that has perimeter 7. So nothing is related to 7, for example, or 9, or 13, or any odd number. So that's how this relation works. Again, there's an infinite number of elements in A and B, so I can't write them all. I can just talk about a few of them when I need to. So hopefully that makes sense. So if we look at this example, we can look. Let's look at the example 10. So 10 is related to 2 numbers, 22 and 14. So we found one counterexample to the definition of a function. So our relation S is not a function. If I scroll up, we can see our first relation, R, that we dealt with, is not a function neither. And you can see it in 2 places. 2 is related to 2 things, 1 and 11. So we know it's not a function there. But also, 5 is related to nothing. Remember, each element needs to be related to exactly 1 element. 3 is related to exactly 1 element. 9 is related to exactly 1 element. That's good. But 2 and 5 are not. So even if it just fails in one case, we can't say it's a function. But let's do an example of a function. So I want to talk about functions now. And functions are a special type of relation. I'll talk about their uses in a second, but let me define what they are. So it's a type of relation where every element of A, and A is going to be the first set. The set on the left is related to, and this is important, exactly 1 element of B. So notice it doesn't say anything about the elements of B, how many elements can be related to them. It could be loads, it could be none, we don't care. The definition of a function only talks about how many elements of A are related to, and that is exactly 1. So let's look at our previous examples here, and we'll see that they are not functions. So here's our example. Oh, wrong color. So let's call it, we used R, we used S, let's call it T. So let A, again, be the natural numbers, and B be Oh, you know what? Let's not make it the natural numbers. Let's make it the integers. That'll be a better example. So let's make A the integers and B also the integers. And then relation T, so we're going to say A is related by the relation T to B exactly when A squared equals B. All right, let's see how this looks. All right, so here's our A, here's our B. Again, there's infinitely many elements in A and B, so I can't draw them all, but I can pick a couple and see what arrows go where. So let's take the element 0, for example. So 0, well, what's that related to? Well, 0 squared is also 0. So under this relation T, 0 is related to 0. What about 1? Well, 1 is related to, well, 1 squared is 1, so 1 is related to 1. Well, what about negative 1? Negative 1 squared, negative 1 times negative 1 is, of course, positive 1. A negative times a negative is a positive. So negative 1 is related to 1. Notice that both 1 and negative 1 are related to 1, but in terms of the definition of a function, we don't care what's going on this side. There's special types of functions that we won't get into where you do care about what's going on this side, but for our purposes, we don't. But you can see every element in the integers has a square. Something like 10, oh, wrong color, 10, its square, 10 squared is 100. So 10 is related to 100. Something like negative 7 is related to positive 49. So negative 7 is related to 49. Since every element has exactly one square, of course it does, this is indeed a function. So since every element of Z has exactly one square, we can say that T is indeed a function. Awesome. And functions are nice because you can think of functions as almost a machine. You can think of them like an input-output thing. Oh, that's not what I wanted. So what do I mean by that? Well, functions as input, output. Well, let's look at that example T. So let me introduce some notation first. So if I want to say T is a function from A to B, well, I'd say T is a function. Well, our A was the integers, and it goes to B, which is the integers. So this was our A, this was our B, and this notation tells me that T is a function. So we call kind of our input set, we call that the domain. And we call our output set, we call that the codomain, the set of possible outputs. So that is our codomain. And if I want to write what's happening here, well, how do we come up with what element a number is related to in A, or sorry, what element in B some element of A is related to. Well, we can do it like this. We could say, well, what do we do to an element of A to get an element of B? Well, we square it. So we could write T of, we can use any variable name we want. It's kind of customary to use X. So T of X equals X squared. So these are elements that you input, and this is the rule for output. So let me show you what I mean, just to get some examples of how to use this. Well, T of 5 is 5 squared, which is, of course, 25. So I'm saying this is the same thing as saying that 5 is related through T to 25. Or something like T of -3 is -3 squared, which is, of course, positive 9. This is the same thing as saying that -3 is related through T to positive 9. So let's do an example. Let's see kind of the power of functions. We can do it in a word problem. We'll build a function to help us out. So, some sort of cell phone plan. Let's do a data plan. So the way it works is you pay $20 a month plus, let's say what? Let's say 10 cents, so $0.1 per megabyte used per month. Okay, so my question will be, what is the cost if you use, and let's do a few examples here. So the first one will be 100 megabytes. The second will be 25 megabytes. The third will be 5,000 megabytes. And what's nice about functions is if you're doing a bunch of calculations where you just need to input different numbers, setting up a function is a really good idea so that you can kind of reuse your work. So let's do it. Let's see if we can develop a function. Well, let's call the function C for cost. And the other thing I want to note is that when I say 10 cents per megabyte, I'm going to say rounded to the nearest megabyte. Okay, so let's build our function C. So we need to pick a domain and a codomain. So if we look at this, well, it's about how many, what's our input? Our input is going to be how many megabytes we use. Well, what type of numbers, if it's rounded to the nearest megabyte, what type of numbers can we put in there? Well, we can just put in positive whole numbers. Again, we're not worried about anything fractional or decimal because we're rounding to the nearest megabyte. And you can't use negative data. So our domain, our set of inputs, is going to be the natural numbers. And our costs, again, it's going to give us a cost per month. And it looks like here, well, we might end up with a cost that isn't a whole number. We might end up with some decimals. So just to be okay, let's make my codomain all real numbers. I could make it, if I like, I can make it rationals as well. That would be fine. It doesn't really matter. You can kind of get away with making your codomain as big as possible because you just need to make sure that every number in your domain matches up to something. So if you include all numbers, you're always going to be in a good spot. You might not hit them all with something from your domain, but that's okay. So let's develop it. So if we put in, remember our input is the number of megabytes we use. We're thinking of this as number of megabytes. Well, how do we calculate the price? Well, no matter how many we use, we have to spend $20. And then, well, we spend 10 cents per megabyte. So we take the number of megabytes, x, and we multiply it by 0.1. So here's the definition of the function that we built. Okay, so here's our function. This is a function that gives us cost as output. Good. Okay. So let's calculate a few values. So we want to calculate first, A asks us, well, what if it was 100 megabytes? So C of 100 is going to be 20 plus 0.1 times 100, which is 20 plus, and you can check, 0.1 times 100 is 10, which is 30. So in the first example, your phone bill is $30. In your second example, we have C of 25. So this is going to be 20 plus 0.1 times 2.5. So that's 20. Or sorry, I did a calculation here when I shouldn't have. That's the next step. This should actually be, we're just plugging in, so this should be 25. This 25 is the same as this 25. This 100 is the same as this 100. Just like this x is the same as that x. Whatever goes in, that's where you put it. And then 0.1 times 25, this is what I was doing a little too quickly, is 2.5. So our final cost is $22.50. And our third example is C of 5,000, which is going to be 20 plus 0.1 times 5,000, which is going to be quite big, which is 20 plus 500, which is $520. So this isn't a very good phone plan for using 5 gigabytes. It would cost us $520. So let's look at one more topic. So I want to talk about combining equations. So let's let f be a function from two sets, a and b, from a to b, and g be a function, again, from a to b. Then, well, for sure, what can I say? I can say that I can make a function, and we'll do an example after I show you kind of the notation. I can add functions together, and all I'm going to do there is I'm going to add the result from both functions. So we can combine f and g to make a new function, f plus g. And there's nothing special about addition. You could subtract as well. You can also multiply f times g. So f times g of x is just f of x times g of x. And just be careful with the use of the brackets here. I know it kind of looks weird, but I just want to say this here is a function. Remember, f and g are both functions, so I'm just saying I'm combining these functions by either adding, subtracting, or multiplying. And you can also divide. You can also say f over g of x is f of x over g of x. We have to be careful here. As long as g of x isn't 0 for any x in A. Because you can't divide by 0, and we don't want a function that kind of screws up for us. So let me give you an example. So let's let f be a function from the reals to the reals, and let's let g be a function as well, again with the same domain and codomain, the reals to the reals. And let me tell you what these functions do. So f takes a number, it multiplies it by 3 and adds 4. G takes the number, subtracts 1, and then squares the result. So let's do the following. So let's find f plus g of 2, f minus g of minus 1, and f times g of, let's do 0. That'll be good. Okay. So, well, remember, f plus g of 2, we're just going to calculate f of 2 and g of 2 separately. So this is 3x, but x is 2, so 3 times 2 plus 4. That's my f. And then my g is 2 minus 1 squared. That's my g. And so my answer is, well, 3 plus 2 is 6. 6 plus 4 is 10. 2 minus 1 is 1. 1 squared is 1. So f plus g of 2 is 11. Let's keep going. F minus g of minus 1 is going to be f of minus 1 plus g of minus 1. Well, f of minus 1 is 3 times minus 1 plus 4. And g of minus 1 is minus 1 minus 1 squared. And 3 times minus 1 is minus 3. Minus 3 plus 4 is 1. Minus 1 is minus 2. Minus 2 squared is positive 4. Minus 2 times minus 2 is positive 4. So f minus g of negative 1 is 5. And thirdly, well, f times g of 0 is f of 0 times g of 0. So that's going to be 3 times 0 plus 4 times 0 minus 1 squared. So 3 times 0 is 0. 0 plus 4 is 4. 4 times, well, 0 minus 1 is minus 1. And minus 1 squared is 1. So our final answer is 4. So f times g of 0 is 4. And just a quick note, sometimes rather than seeing a dot, you'll see an actual times symbol. Or you might just see FG like that with no symbol in between them, just like you would for multiplication. So you'd see all of those things. And then maybe let's do kind of a fourth example. So let's find a simplified formula for f plus g of x and f times g of x. Okay, so let's do it. And here's the solution. So I know f plus g of x is, of course, f of x plus g of x. F of x is 3x plus 4. G of x is x minus 1 squared. Now let's simplify this as much as possible, so we'll combine like terms. Let's expand x plus 1 squared. So remember, x plus 1 squared is x minus 1, not x plus 1, my mistake. X minus 1 squared is x minus 1 times x minus 1. So we'll do, we'll expand this out using distributivity. So x times x is x squared. X times negative 1 is negative x. Negative 1 times x is negative x. And negative 1 times negative 1 is positive 1. So x minus 1 squared is x squared minus 2x plus 1. So this is 3x plus 4 plus x squared minus 2x plus 1. Let's combine our like terms. Well, 3x minus 2x is 1x. In fact, maybe let's write it in decreasing power order. So we'll do x squared first. That's just by itself. And then we have 3x minus 2x is plus 1x. And 4 plus 1 is 5. And you can check, just to see how this works. Remember, f plus g of 2 was 11. So let's see if we get the same answer. So we get 2 squared plus 2 plus 5. Remember, this is our x, right? X is 2, so wherever we see an x, we put in our 2, which is 4 plus 2 plus 5, which is, of course, 11. So it works the same. So let's do f times g now. So this is 3x plus 4 times x squared minus, x squared, minus 2x plus 1. So this is f of x. This is g of x. I just simplified g of x so it's easier to multiply. That's x minus 1 squared. I just simplified it a little bit. So we'll use distributivity. So this is 3x times x squared is 3x squared. 3x times 2x, 3 times 2 is 6. X times x is x squared. Sorry, guys. Small mistake. 3x times x squared is not 3x squared. It is 3x cubed. Because x times x squared, well, that's x times x, which is x multiplied by itself 3 times. So it's 3 times x cubed. And then 3x times minus 2x is minus 6x squared. And then we have 3x times 1. Well, that's easy. That is just 3x. And then we'll do the other way. 4 times x squared is 4x squared. 4 times 2x, times minus 2x is minus 8x. And 4 times 1 is, of course, 4. And let's simplify this. So we'll do our x cubed first. There's just one of them, 3x cubed. Let's do our x squareds, 6x squared. Negative 6x squared plus 4x squared is minus 2x squareds. Then we have 3x minus 8x is minus 5x. And we just have the 4 left over. And this is our simplified formula for f times g of x. So there we go. That's how we can combine functions to make new functions.